Before we continue with the course, let me share some thoughts of what we have done so far, because we learned a new language. So basically, so far in the course, we learned the language of Sturm-Liouville problems, and we talked about eigenvalues, and we talked about eigenfunctions, we talked about the Rayleigh quotient, and we also learned that these Sturm-Liouville problems, they form series solutions to PDEs, and these series solutions are approximations. They get very close to the real function. However, there can be jumps, and at jumps we have Gibbs phenomenon, where the solution really oscillates very, very quickly. So what happens next in the course is we take this new language, which we just learned, and we apply it to more and more complicated, but also more and more interesting problems. For example, instead of a string, we will look at a plate, of a vibrating plate or a vibrating drum. Instead of heat conduction in a rod, we will then look at heat conduction in a three-dimensional object, like a wall, through a wall. Of course, things get a little bit more complicated, and we will not be able to get away with sine and cosine functions anymore. Instead, we use their cousins, and their cousins have fancy names, so we will use Bessel functions, we will use Legendre polynomials, we will use Hermite polynomials, we will use spherical harmonics, we will use Laguerre polynomials and Chebyshev polynomials. So these are all fancy words for basically the idea of sine and cosine. So I call them generalized sine and cosine functions. And since you have seen how sine and cosine work in a Fourier series, I think you understand the principle, you understand the main idea behind all these fancy names.